All right, yeah, I think we're recording now. All right, so I'll start. So I just wanted to share with you a few of the projects I worked on here at Avi Networks. Oh, and I'm Kunal, by the way. So the first project I worked on was an SE Datastore diagnostics tool. And basically the problem that this was addressing was when something's wrong with the SE Datastore, you don't really know what's going on, right? And the process to understanding what's going on involves diving through logs and running your own tests. It's pretty time consuming, and it'll be a lot more convenient if there's one script that you could run to get all this information. So that's where my solution comes in. And it basically is two tools that run in your controller. One is a diagnostics tool, and one is an object dump tool. And I think the best way to kind of showcase this is through a demo. So I'll run that through real quick. So right here, I'm just SSHing in the controller. Nothing too unfamiliar. And then there'll be a script called gRPC datastore.py. And right here, I'm just running the diagnostic side of that. So right here, you just get the basic diagnostic information. That includes current version, min version of the SE Datastore, uptime, and setup. And then for the service engines, it includes name, UUID, version, uptime, and state. And state includes like sync, disconnected, subscribe, fast forward, and subscribe live. And subscribe live is kind of like the golden state because you don't really, like once it's in subscribe live, you know like nothing's really wrong. So beyond that, what I'm doing here is I'm grabbing that one SEUID, and you can kind of you can search for one service engine or multiple service engines. This isn't a super useful feature right here in this particular example because I only have two, so it's not that difficult to see both. But if you were to have like 20, 30 service engines, this would be a super useful function. And then in addition to that, you can grab the detail, and this will basically just show you the detail for the SE Datastore and its service engines. So as you can see right here, you get the applied if time, like the average applied if time, total gets. And for the service engines, you're not going to see a lot of detail right now because they're all in subscribe live. But so all you get is like the time that it was in subscribe live. But if you were to be in subscribe fast forward, you would see like a bunch of other statistics. And then similar to before, you can also go for certain service engines after you got the detail. And that basically sums up the diagnostics portion of this tool. And the next portion is the object dump. So right here, I'll run that real quick. And this will basically dump out all the objects in the service engine data stores and the SE Datastore as well as the version that it's in. And what you can also do here is you can also grab the objects in only the data store or the service engine data store. So right here, I'm just printing out the data stores objects. And then right after this, I'll print out just the service engine data stores objects. There's also a Confluence page so you can kind of understand these tags. And then similar to the previous tool, you can basically pick and choose which service engines you want to see the objects from. Again, it's not super useful here where there's two service engines to work with, but when there are more, it'll be super useful. And there you get the objects in that service engine. One more useful feature of this tool is that you can grab the object UUID and basically ask for the details of that object. So what I'll do here is I'll say, basically show me the contents of this object, of the specified UUID. And in there, it'll dump out all these contents. So right here, you can see if you go all the way up, it'll give you for this service engine, you have the object which has these contents and whatever version you're at too. And you'll get it for all these service engines and the SE Datastore. And this is useful to see if there's any mismatch in what the objects contain. And then also if there's an object that doesn't have, or there's a data store that doesn't have this object, it'll just say this, the SE Datastore doesn't have this object. And that basically wraps up this diagnostics tool. I think The next steps is getting this implemented in the metrics DB. That's unfortunately something I couldn't work on here, but those are the next steps for this project. So that was that basically wraps up part one of this. Are there any questions on that specific project? Otherwise, I can move on to the next project. So the next project was one that was super interesting for me. It's basically exploring calling Go code inside of Python. And so the problem this was trying to address was redundancy and inefficiency. So the example we worked with was calling, was getting diffs basically. Go's version of getting diffs is way more efficient than Python's. And the way the code base is set up is that you currently have to write code in many different languages and they all kind of do the same thing. Raul gave me the example of for getting diffs, you have to write in C++, Python, and Go. And Go is always more efficient than the other two. But just so you can call it in Python, you have to write it in Python. So the simple solution was to call this, call Go's methods in Python without having to like explicitly rewrite anything. And this works by using shared object files and libraries. And the reason this was more of an exploration than a project, well, it turned into a project after it started working, was because we weren't exactly 100% sure if this would work. So I'll just walk you through the first steps of this project. And so the first steps was to call a simple function in Go, which took two ints and summed them, and print that out in Python. This was super straightforward. You just have this function add in Go, and it'll print out the sum of those two integers in Python. The next function was where things got a little more tricky. We have this function named bill, which takes a string, and it just says bill says then whatever the string is. This is where we kind of opened a can of worms and like dug into all these C types, and we realized, okay, this gets a little bit deeper than just calling a function. You have to kind of these types. And then the other steps were kind of understanding behaviors that are kind of exclusive to Go and are not there in Python, like defer and other error handling that we do in Go. The next steps was getting get diffs to work in Python, Go's method. And this involved working with different C types. We had a test for a lot of memory. And I think actually the last 2.5 weeks was working on getting the making sure it's as durable as possible. So I'll just give you a quick walkthrough of where we are right now. Can you guys see that code? Or is there two? Okay.
Yep.
Yeah,
the lights on. Yeah.
This is what it looks like on Go side. You have a native Go function called hello world native, and it just returns hello world. And this is basically what we're working with. It's exporting this hello world function to C and basically from C to Python. And this is the Python side of it. You import C types, you load up this library, set the return type, and then from there you just call the function. And just to show you this workshop quick, I'll run. Okay, hello. So really what we're doing in Go is we're taking the existing methods and a quick wrapper around it so it can be passed to C. I'll just walk you through the extensive tests we did on getting this to work. So initially we were just working on passing protobufs through once we got the actual few methods to run. And as you can see, it was it took a while to get protobufs through, and here especially table. Have the majority of time running the shared object method, but you also have these other factors that are contributing to the runtime, and we try to close it as much as possible to get it as efficient as possible. From there, we moved on to memory tests. This are also very extensive. We basically check if you have multiple scripts that are loading the library. If it's basically ballooning up the memory use. We found that no, it doesn't, and actually just process calling. We also check to see if passing 10 meg, 50 meg protobufs through Python to go and back create any memory leaks, and we found that after about 500 to 1,000 iterations, all the memory usage plateaued out. So beyond that, we got to what was kind of like the most exciting, but it's also the most practical diff test. So up here you can see in our first stages of testing, Go was running at about anywhere from 4 times slower to 10 times slower, which is pretty inefficient. It was great that we could call Go's code, but it's also not really practical if it's taking 10 times already out there. So the rest of these tests were kind of breaking up the steps that we're taking. We're basically seeing how long these steps take. Found some pretty shocking discoveries. We found that changing the return type would drastically take time. So in this next iteration of the test, we changed the return type, and now we've got it down to 2. And from there, we changed it. Instead of returning bytes, we returned a pointer to a character. And we got that runtime down to just 2.1 times. From there, we broke. We still continue to break up how long certain steps are taking. This is where the most shocking discovery was made, and I think that's kind of the next steps of this project. And it's right here in on Go side, it's the protocol to map and then get this. Just to give you a quick background, getDiffs optimizes the actual Go function that's called, and protocol to map is converting whatever we send from Python to a map so it can be called in getDiffs optimized. As you can see here, it takes the majority of time is spent in actually converting the protocol to a map, which we really hope to get that down because it basically eliminate that time, get getDiffs optimized working just on protocols instead of having to convert to a map. Can get this time down to 1 time or even faster than Python. And from there, I think we'll move on to what is the most exciting test because it really showed how practical this is. And this is the nested object diff test. This is where Go's logic becomes way more efficient than Python. Just to give you a quick background again, testperf is a function that basically has a bunch of nested objects, and within those nested objects, creates a whole bunch of other nested. So it can be a little confusing. The first number in the parameter, the bigger that number is, the more level 1 nesting. And the smaller the second number is the greater the sub-nesting. So already right off the bat in the first test, we're seeing that Go and Python's logic is returning the same thing, but Go is actually doing it 329 times faster than Python is. And when you move further down the list, you can see that Go is consistently going faster than Python when it comes to nesting. But what's even more interesting is when you get to this part, when Python and Go start returning different results. This basically means that there's so much nested objects going on that Python is kind of timing out here and saying, okay, this protocol is completely different. We're just going to say the entire protocol is, which may not be so bad for this, but when you're actually trying to apply those diffs, it's very expensive. On the other side, Go is taking less time and is returning a more accurate answer. So all the way down to here, which is definitely the most sensitive test you could do, Go's returning the full on 144 length answer, while Python is just saying entire protocol is different. That's the entire tip. That's why I think Go really shines is right now getting these nested object diffs. Go is doing significantly better than Python. So from here, the next steps is getting the protocol to map down to 0 basically, so we can get even basic non-nested protocols, getting the diff logic working just as fast as it is in Python. That basically wraps up this part of the project. Any questions?
Initially, the first numbers you said Go was worse than Python, but I mean the diff Go was better than Python.
Right. So I'll just go back to that real quick. You're talking about this table and then the next table I showed on the next slide, right? Right. So these tests, I should elaborate on this more. This test is saying have 2 large protocols of 1, 10, 33, and 50 megabytes, right? And you just add like a simple dash change to one of the fields. So it's a super trivial diff compared to the other sheet. But in that, we're getting Go is running at about 2.1 times slower. Once we get the protocol to map time down to 0, it'll basically be just as fast, if not faster. But these tests are different. It's basically where you're having a bunch of nested objects. That's where Go's logic is much faster. That's why we're getting a faster time on Go.
Second one is actually testing the diffing logic in terms of there's actually a lot of diffs that it needs to compute. There, the Go's algorithm is much more efficient, and
So the NT and Go wasn't the big
that's the problem. The first test, however, is trying to simulate pumping a lot of data into Go and sending a lot of data. There's actually not much work going on there. Not really much to compute, but just transporting data, parsing the data, sending the data back was more overhead than the actual logic itself. Right. So with this, we know that the logic itself is much more efficient. It's just how do we take care of the passing data, serializing data, reduce those costs. Then at worst, passing large data will basically, if there's nothing to do, it will be 1x, same as Python, let's say. If there's really work to do, that's going to be much more efficient.
Right.
Just to add to that too, I think one of the great things we talked about with the application of logic, the reason why Go's bindings are so much better is because Raju is kind of incredible algorithm on creating these diffs different way, a totally different algorithm altogether. And we thought about, should we just reproduce that in Python and write it again? But even then, we already have discrepancies how solid the Go's bindings are actually a lot more solid than the Python's bindings. Like we have more bugs in Python. So with this, the whole point is, the diff logic is already way better. If we can get just a simple, changing a name of a PB to be exactly one time, then it's strictly better. And now we have one code base. So across the board, it's a superior way to do things where we can just call one code base. So I think that's another reason why we focus a lot on, like, if we have 100 meg protobuf and we change a name on that field, let's make sure that that's at least at parity with Python, because there's a little more overhead to transfer it into the .so and do that. But I think we have a strong path towards getting it at exact parity.
What are your biggest challenges?
I think biggest challenges kind of came in steps. The first challenge was really kind of getting used to understanding how Avi's code was kind of written, and that was where I was grateful that I got to work with a diagnostic, because that was I knew how to write everything. It was just kind of understanding, okay, this file does this, like how does Avi write their code, and that helped me overcome this challenge, which was now I don't exactly know what I'm writing. I'm working with all these new C types. I've never worked with C, but now I have the understanding of how Avi writes code.
To learn some stuff.
I definitely did. I think definitely I love the second project the most. I definitely learned the most from it, and it inspired me to take some classes. I want to see how this stuff works around the world.
If you don't know C, you don't know programming.
If you don't know C, you're not a programmer. You gotta know C.
And if I can just say some words, I got the pleasure of working with Kunal pretty closely, and I was really impressed from the very beginning to the end, like incredible ramp. By the end, like we had some pretty low level, like we were manipulating bytes, we're passing buffers back and forth between, Go, and Go has to encode it a certain way so that it goes down to C, and then Python's gonna load it and load it into Python. And we had some tricky bugs. Kunal had really good attention to detail, helped us like solve a lot of these things and get all the way to actually calling diffs and running all these. So yeah, it was really cool to see that. A great job.
What did diff test do with the comparing the objects to objects?
Is that specifically in this slide or this slide?
Or in general, the diff test?
Right. So in general, we kind of work with passing protobufs of varying size from Python to Go and then back. What the differences were. So we kind of have different.
You mean the size of the objects or the time that take?
So we measure the time it takes based on the size of the. So like right here we have a 1 megabyte protobuf being passed from Python to Go, and then we want to see basically how long does it take for it to come back with the right. So right here it took 72 milliseconds, whereas in Python alone, 24.
Okay, another question is how was the SO file created from the Go?
So basically, I read like an entire article. It's really simple. You basically have your Go file, right? Have this little export hello world, and you basically build a Go in a certain way where it spits out a shared object file that we call. I forgot the specific command, but it's somewhere in Go build, and then there's different build modes. Plugin, shared lib C, the shared lib C will give you a data, so it'll compile it down to you scroll up to the top of this file, of course, and then it has an import C at the very top on line. So then when you put like a comment, the export function name, it knows to compile this down into C, and it'll pull it into the data. So
And the dependency of that Go shared lib. Here. If you load the library here, so ESO may depend on some other.
yeah, and it's kind of cool. We did some tests on that too, and like it's pretty efficient. So if you like import a bunch of stuff you don't need, it'll just root out what you don't need. And the package that. All right, if there aren't any more questions.
Yeah.